Our ancestors looked up at the night sky with a mixture of awe and fear. The vast expanse above them was both a source of wonder and a reminder of their own smallness in the grand scheme of the universe. They saw patterns in the stars, the celestial dance of the planets. These patterns were not just random, they seemed to tell stories that were passed down through generations. These celestial objects seemed to follow a rhythm, a cosmic ballet different from the rules governing our world. The stars moved in ways that were predictable, yet mysterious, a dance choreographed by forces beyond human comprehension. Ancient civilizations wove myths and legends around these celestial wonders. They created star maps and astronomical artifacts, trying to make sense of the heavens. They imagined gods and goddesses, powerful beings residing in the heavens. These deities were thought to control the fates of humans, their actions reflected in the movements of the stars and planets. The universe was a place of mystery, a realm beyond human understanding. The Milky Way, a river of stars, was seen as a pathway to the divine. Ancient cultures developed intricate systems to explain the movements of celestial bodies. They built observatories and created instruments to track the stars, seeking to unlock the secrets of the cosmos. They created calendars based on the cycles of the sun and moon. These calendars were essential for agriculture, religious ceremonies, and daily life, linking the heavens to the rhythms of the earth. They believed that celestial events held power over earthly affairs. The alignment of planets, the phases of the moon, and the positions of stars were all seen as indicators of future events. The appearance of comets, the eclipses of the sun and moon, these were seen as omens, signs from the gods. Such events could herald great change, for better or worse. For centuries, this celestial tapestry fueled the human imagination, inspiring both art and religion. Temples were built to align with celestial events, and rituals were performed under the night sky. Yet for all their beauty and complexity, these ancient cosmologies were limited by the tools of observation available at the time. The naked eye could only see so far, and early telescopes were rudimentary. The human eye could only perceive so much. Despite their best efforts, ancient astronomers could not fully grasp the true nature of the cosmos. The heavens remained a realm apart, governed by rules that seemed fundamentally different from those governing our everyday lives. This separation between the celestial and terrestrial worlds was deeply ingrained in human thought. This division between the celestial and the terrestrial would persist for centuries, shaping humanity's understanding of the universe. It influenced philosophy, science, and religion, creating a worldview that saw the heavens as a place of perfection and the earth as a realm of imperfection. It would take a revolution in scientific thought to bridge this divide, to reveal the underlying unity of the cosmos. The work of astronomers like Copernicus, Galileo, and Kepler began to unravel the mysteries of the heavens, showing that the same physical laws applied both above and below. The Babylonians were among the first to systematically record celestial events. They created detailed star charts and clay tablets that tracked the movements of planets and stars over centuries. These records were used to predict lunar and solar eclipses with remarkable accuracy. In Egypt, the pyramids were aligned with specific stars, reflecting the Egyptians' belief in the connection between the heavens and the afterlife. Hieroglyphs often depicted celestial events, showing the importance of astronomy in their culture. The Greeks made significant strides in understanding the cosmos. Philosophers like Ptolemy developed the geocentric model, which placed the Earth at the center of the universe. This model, though incorrect, was a crucial step in the development of astronomical thought. In China, astronomers created sophisticated instruments like the armillary sphere to observe the heavens. They produced star maps that were incredibly detailed, and their observations were used to guide agricultural practices and predict celestial events. The Mayans built observatories to study the sky and developed a complex calendar system based on their astronomical observations. Their understanding of celestial cycles was so advanced that they could predict solar and lunar eclipses with great precision. In India, ancient texts like the Vedas contained detailed astronomical knowledge. Indian astronomers created star charts and developed mathematical techniques to calculate the positions of celestial bodies, influencing later astronomical studies. Islamic scholars preserved and expanded upon the astronomical knowledge of earlier civilizations. They invented tools like the astrolabe and celestial globe, which allowed for more precise observations and calculations of the stars and planets. These early astronomers laid the groundwork for future scientific discoveries. Their meticulous observations and innovative tools were the first steps in humanity's ongoing quest to understand the universe. The scientific revolution, which began in the 16th century, marked a profound shift in our understanding of the universe. This era was characterized by a surge of intellectual curiosity and a relentless pursuit of knowledge that transcended the boundaries of traditional thought. It was a period of intellectual ferment, driven by new observations and a willingness to question long-held beliefs. Scholars and scientists began to challenge the established doctrines, seeking empirical evidence and logical reasoning to explain natural phenomena. At the forefront of this revolution stood Isaac Newton, a towering figure whose insights would reshape our view of the cosmos. Newton's contributions were not just limited to physics. His work spanned mathematics, astronomy, and even alchemy, making him a polymath of unparalleled influence. Newton's laws of motion, published in his masterpiece, Philosophiae Naturalis Principia Mathematica, provided a unified framework for understanding the motion of objects both on Earth and in the heavens. This monumental work laid the foundation for classical mechanics and introduced concepts that would become fundamental to the study of physics. These laws, elegant in their simplicity, stated that objects in motion tend to stay in motion unless acted upon by an external force. This principle, known as inertia, was a radical departure from the Aristotelian view that objects required a continuous force to maintain motion. Newton's second law, which states that force equals mass times acceleration, provided a quantitative description of how forces affect the motion of objects. This law allowed scientists to predict the behavior of moving bodies with unprecedented accuracy. And Newton's third law, which states that for every action, there is an equal and opposite reaction, explained the interactions between objects. This principle is vividly demonstrated in the operation of rockets and the simple yet profound Newton's cradle. These principles, seemingly self-evident to us now, were revolutionary in their time. They provided a new lens through which to view the natural world, challenging the Aristotelian view that had dominated Western thought for centuries. The Aristotelian framework, which posited that the heavens and the earth were governed by different sets of laws, was upended by Newton's insights. His work demonstrated that the same principles applied universally, from the fall of an apple to the orbits of planets. Newton's most profound insight, however, lay in his law of universal gravitation. This law unified the celestial and terrestrial realms under a single, elegant principle. This law stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This was a groundbreaking realization that connected the motion of celestial bodies with everyday experiences on Earth. This simple equation, F equals gm1m2 over r squared, had profound implications. It provided a mathematical framework for understanding the gravitational forces that govern the motion of planets, stars, and galaxies. It meant that the same force that caused an apple to fall from a tree also held the moon in orbit around the Earth. This realization bridged the gap between the heavens and the Earth, showing that the same natural laws applied to both. It meant that the planets, instead of being moved by celestial spheres, were locked in a cosmic dance governed by the invisible hand of gravity. This new understanding of the universe as a coherent, interconnected system was a monumental shift in human thought. With Newton's work, the artificial division between the celestial and the terrestrial was shattered. The universe was revealed to be a single, unified entity, governed by consistent and predictable laws. The universe was no longer a realm apart, governed by capricious deities. Instead, it was a grand machine, operating according to precise mathematical laws. This mechanistic view of the universe would dominate scientific thought for centuries to come. Instead, it was a grand machine, operating according to precise mathematical laws. This Newtonian universe, clockwork in its predictability, would inspire generations of scientists and philosophers. The idea that the universe could be understood through mathematics and observation laid the groundwork for the scientific method. This Newtonian universe, clockwork in its predictability, would inspire generations of scientists and philosophers. It provided a framework for exploring the natural world that emphasized observation, experimentation, and mathematical analysis. It would also lay the groundwork for the technological advancements that would transform human civilization. The principles of Newtonian physics would drive the innovations of the Industrial Revolution, leading to the development of machinery, transportation, and technologies that reshape society. The 19th century witnessed another great unification in physics, this time in the realm of electricity, magnetism, and light. This period was marked by a surge of scientific discovery and innovation, as researchers delved into the mysteries of these fundamental forces. These phenomena, once considered separate and distinct, were woven together by the brilliant Scottish physicist James Clerk Maxwell. Maxwell's work was revolutionary, as he built upon the foundations laid by earlier scientists like Michael Faraday and André-Marie Ampère. Maxwell's equations, a set of 4 elegant equations, described the behavior of electric and magnetic fields and their interactions with matter. These equations were not just mathematical abstractions, they provided a comprehensive framework that could be applied to real-world phenomena. They predicted the existence of electromagnetic waves, disturbances in these fields that travel at the speed of light. This was a groundbreaking revelation, as it suggested that light itself was a form of electromagnetic radiation. Maxwell's theory unified electricity, magnetism, and optics into a single coherent framework. This unification was a monumental achievement, as it bridged the gap between different areas of physics and provided a deeper understanding of the natural world. It revealed that light itself is an electromagnetic wave, a ripple in the fabric of the electromagnetic field. This insight transformed our understanding of light and opened up new avenues of research in both theoretical and experimental physics. This realization had profound implications for our understanding of the universe. It meant that the same principles governing electricity and magnetism on Earth also applied to the vast reaches of space. It meant that we could study distant stars and galaxies by analyzing the light they emit. By examining the electromagnetic spectrum, astronomers could infer the composition, temperature, and motion of celestial objects, vastly expanding our knowledge of the cosmos. It paved the way for the development of technologies like radio, television, and wireless communication, all of which rely on the transmission of electromagnetic waves. These innovations revolutionized communication, making it possible to transmit information across vast distances almost instantaneously. Maxwell's work represented a triumph of the human intellect, a testament to the power of mathematics to describe the workings of the natural world. His equations not only explained existing phenomena but also predicted new ones, showcasing the predictive power of theoretical physics. It also highlighted a recurring theme in the history of physics: the unification of seemingly disparate phenomena under a single set of laws. This theme of unification has driven many of the greatest discoveries in science, as researchers seek to find the underlying principles that connect different aspects of the universe. This quest for unity, for a single theory that could explain the workings of the entire universe, would continue to drive physicists in the 20th century and beyond. The legacy of Maxwell's work lives on, inspiring new generations of scientists to explore the fundamental forces that shape our world and the cosmos. The dawn of the 20th century brought with it a revolution in physics that would challenge the very foundations of our understanding of the universe. 2 revolutionary theories emerged, each profoundly altering our view of space, time, and the nature of reality itself: Einstein's theory of relativity and quantum mechanics. Albert Einstein, a patent clerk working in Bern, Switzerland, published his groundbreaking theory of special relativity in 1905. This theory, born from the realization that the speed of light is constant for all observers, regardless of their relative motion, shattered the Newtonian concepts of absolute space and time. Einstein showed that space and time are not separate entities but are interwoven into a 4-dimensional fabric called spacetime. This fabric, far from being static, is warped and curved by the presence of mass and energy. A decade later, Einstein would further revolutionize our understanding of gravity with his theory of general relativity. This theory described gravity not as a force acting at a distance, but as a curvature of spacetime itself. Massive objects like stars and planets create depressions in the fabric of spacetime, much like a bowling ball placed on a trampoline. These depressions dictate the paths that objects follow through space, explaining the force of gravity.